Hi, welcome to 3.5 for fundamental subspaces. This is the first part of probably 2 to 3 videos for this section. I'll be honest, this is the third time I've tried to film this over the last, I think, week actually, in real time. My phone keeps running out of storage. I've got to reset it or something. That's what I film on. And so hopefully this thing will film all, otherwise you won't see this at all, and you'll see the next video after I record next week because I'm going to be too frustrated to try again today. So in this video, we're focusing on the 4 fundamental subspaces, which you'll see here. This is listed in the text. He actually writes this out, I think, very cleanly on page 129. And what we'll start with is looking at a matrix R0, so something that is in reduced row echelon form. Row of zeros is in my last row, and going through each of these spaces, identifying what the dimensions of this space, each space is. We know that dimension is counting the number of vectors and the basis for that space. And so we're going to go do that, identifying how many vectors, what is the basis for the space for each one of these. Now, there is 2 spaces that you should be really familiar with by this point in the text, which is column space and null space. Null space is kind of newer to Unit 3, but it's something we've been doing all unit. Column space we've seen from Unit 1. This is looking at the independent columns in my matrix. Row space we kind of hit on a little bit in Unit 1. We talked about the ideas that the dimension for both the column space and the row space, the ranks are the same. And so we'll kind of see that happen. We'll kind of talk about where that happens. And then the left null space is going to be what's newer. And in this section, we'll actually see a big application of linear algebra and matrices to the Kirchhoff formula. And the Kirchhoff, I believe, I want to say algorithm, but it's Kirchhoff's current law in terms of electricity and current. So that kind of form of the word. So we'll actually look at that, which as someone who teaches a logic class, a discrete mathematics class, and bringing in a little bit of graph theory, I think it's really interesting to bring this in because there's a lot of connections between linear algebra and incidence, edge matrix, and table, and kind of the connections there. So we see that with left null space will come in to that problem, and so you'll see that. At the end of part 1, we've been looking, we would have looked at this reduced row echelon form. Part 2, we're going to look at, well, does all of this stay the same if we were to look at the original matrix? And then that'll lead us into essentially part 3, if needed, into the fundamental of linear algebra, fundamental theorem. There we go, sorry, brain fart. I was thinking fundamental theorem of calculus and I couldn't think about it in terms of the form. And so we'll look at the fundamental theorem of linear algebra, which there are 2 parts like calculus, as well as very similar to the fundamental theorem of algebra. So we'll kind of see that as we go through and look at these spaces and really kind of define that. So without further ado, let's break down each of these spaces. So starting with row space, one way to think about row space is that we are really looking at the column space of A transpose. So in terms of my matrix R0, if I was to transpose this, we're essentially looking at and seeing, well, how many column vectors are independent. Now we can do that by looking at this in terms of its current row form and really just kind of analyzing the rows and saying, okay, is it possible to write the rows as combinations of each other? We're essentially identifying how many independent rows are there. And when I'm looking at this in terms of the row picture, going row by row, notice how I have a pivot here and a pivot here, and because there's no lineup, it doesn't zero out or anything like that, there's no way that this second row is a combination of the first row. If we approach with the same mindset that we used in Unit 1, if my first row is automatically independent, the second row would have to be a multiple of the first, and it's clearly not because of the zeros. So I have 2 independent rows, and the only way to get this row is by multiplying these by 0. There's no linear combination of these 2 things without multiplying by 0 to get this one. And so these are completely independent. I have 2 independent rows, which means in terms of my basis, I would have those 2 rows as my vectors, and therefore its dimension would be 2. So the dimension of the row space, so the dimension of this would be equal to 2. There are two vectors in the basis of the row space. Now, what we're looking at is you'll notice that dimension is equal to R. Well, R stands for the rank of the matrix. So one thing I hadn't filled out yet, we'll fill out now, is that my matrix is originally a 3 by 5 matrix. And you'll notice that there are two pivots, so my rank is 2. And notice how the rank matches the number of vectors in the basis of the column space. The basis of the row space. Looking at the C. And so how those two things match. And so that's what we're kind of showcasing here as we go through. And so when we identify the column space, we should also see that there are two vectors in the column space that form the basis of the column space. And therefore would have a dimension of R2 as well. And we can also see that fairly quickly because when I'm looking at this, one of the reasons why we didn't transpose it, if I'm looking at this, again, in terms of columns, I have one independent column and I have a second independent column. There are 3 free parameters or 3 free variables in here. And we can even see and kind of tell that when I'm looking at my very first column, this second column is a combination of this one. It's a scalar multiple. This is a scalar multiple of the first one, but this one is not. The final column is a combination of both of these. So that means the column space would have 2 vectors in its basis, and that would be 1, 0, 0, 0, 1, 0. Notice that in terms of the identity matrix, that's found in a 2 by 2, which is an R by R, 2 by 2. And so looking at the column space for this, the column space would contain just 2 vectors as a basis. And so its dimension would be 2. Again, lining up with the rank, the number of independent, number of pivots, the number of independent columns. And so that matches what our discussion was way back in Unit 1, that the row space and the column space have the same dimension. They're both equal to the rank. Now getting into something that's a little bit closer to Unit 3, being the null space, when that was introduced and discussed, when I want to look at the null space of this matrix, again, we're trying to take into account the free variables or the special solutions, and we actually just discussed what those look like in terms of the combinations of the columns themselves. For example, the very first special solution I would list out as -3, 1, 0, 0, 0. Again, taking the opposite, it's the multiple in terms of the combination. The second special solution would be -5, 0, 1, 0, 0. And then my third special solution for the final would be -7, 0, 0, -2, 0, 1, being the final column. And hopefully I miscounted. Let's see. That was right, it's in the 4th spot. I had one too many zeros, so 1 there. 5, 1, 2, 3, 4, 5. So that lines up there. So -7 lining up with that pivot, -2 lining up with that pivot, both of these being zeros. And so these 3 vectors are all linearly independent. They would span the null space. They form a basis of the null space. Notice how there are 3 vectors, therefore this would have a dimension of 3. So the dimension of the null space, and I'll just say n of a, or n of r, 0, excuse me. This would be equal to 3. And if you're paying close attention to the formulas that are given, notice this is the number of columns minus the rank. Because there are 2 independent columns, there has to be 3 variables, 3 free variables, 3 special solutions, meaning the dimension of the null space would have to be 3. And so if I take 5, subtract off its rank, notice how that works out. So as we have this formula of, for any n by n matrix, the dimension of the null space should always be n minus r, always. And again, we'll verify that when we start looking at a matrix that's not in reduced row echelon form. And so that's the dimension of my null space for this matrix. Now the final matrix that we haven't discussed too much yet, but we will, is the left null space. And the idea here is very similar to the row space. We're looking for the special solutions of the rows, not the columns. And one of the ways that we can analyze that is by taking the transpose of the matrix. And so here I'm actually going to do that now and say, okay, well, the first row becomes the first column. 7, I always tend to mess this up, as you know. So I'm going to write that here. And if I'm looking across the board, we want to try to solve this problem I'm looking for the solutions to R0 transpose is equal to 0. I'm looking for y. I want to know what is y1, y2, and y3. That if I perform this multiplication, we would get 0, 0, 0. 0, 5 zeros, excuse me. I just got underneath with the shift. So I want to figure this out. Well, if you notice just from the multiplication, just from the first row, this becomes y1 has to be equal to 0. Notice 3y1 also still equal to 0, so y1 is equal to 0. Still equal to 0, free variables. The next pivot point tells me that y2 also has to be equal to 0. So notice the one thing that is free, the one thing that can be anything we want it to be, would be y3 when I'm going through and doing my multiplication. And so one of the solutions to this would be 0, 0, y3, and it is in fact the only solution to the null space. Really the solution to this equation, telling me that there's one vector in the basis of the null space, left null space, and its dimension would then have to be 1. And if, again, you're paying close attention to the format, if this is a 3 rows, 3 minus the rank of 2 holds true here. There is one solution. I have one row of zeros. Therefore, when I transpose it, I'm going to have one free column. Both columns here have pivots in them. So I would have a dimension 1 in the basis of the left null space. There's one vector there. One non-zero solution. Because y3 can be anything. We can take any scalar of that to create a solution. So this is looking at the dimension and focusing on dimension. So just recall that dimension is the number of vectors in the basis. So we're trying to count the number of vectors because it doesn't matter which basis you're looking at for a space. Remember, bases are not unique. The dimension has to be consistent though. So the dimension is always the same. So this would always have to be true. And so again, we're going to check that by taking in the next video, looking at the matrix for A and kind of confirming that all of this holds true, even if we were to look at A instead, and going back into the original matrix. So let me know if you have any questions, and hopefully this video recorded completely.